So again, good afternoon for the people who are watching us on recording, or they're going to watch us later on. So to remind all of you that lab test 3 is next Monday. Make sure you attend your session. If you register in the morning, please attend the morning session. If you register on the afternoon, please attend the afternoon sessions. And last lectures, we discussed the computational complexity, and computational complexity will be included in the lab test 3. So we discussed how we break down any method to elementary instructions, then count these elementary instructions and find the big O notations and find the complexity. We discussed different type of big O notations about linear time complexity, constant time complexity, logarithmic time complexity, linear logarithmic time complexity, and we saw that exponential is the most expensive time complexity method, and we should try to avoid exponential time complexity if we are designing any method. Today, we'll start a new topics. We'll start the recursion. Recursion is very, very important topic and is a core for many other courses. Today we will try to break down the recursions and we will try to define So we'll try today to cover the recursions and break down the definition of the recursions to make it easy for us to understand it. We will consider the recursive algorithms and compare it with iterative algorithms. We will see what is the content of any recursive method. Recursion is one of the topics. It's well known that it's hard to understand, but we will try today all together to break it down these topics to basic informations, and we'll try also together to build recursive methods, okay? And the best practice to learn recursion is to look at the examples, learn from examples. All of us learn from examples. So we're gonna see a lot of examples today and next lectures about the recursive methods and how other people build the recursive methods. And we're also gonna see how we can analyze the recursive methods and trace the execution of any given recursive algorithms. From the textbook, you can, or from the notes, you can see chapter number 8. The note is in the Moodle. You can download it and see chapter number 8 is talking about recursion algorithms. If we need to define recursion, we define it as an operation in terms of itself. Or you can say solve the problem using the recursion depend on solving a small occurrence of the same problem. So you have the same problem, a small version of it. If you are able to solve the small version of the problem, you can solve the big version of the problem. Recursion algorithms find the solution of any given problem by reducing the problem to the smaller version of itself. So we're not changing the problem. We are taking the big problem, we try to reduce it to the small version of this problem and find the solution for that problem. We're going to see today direct recursion. Methods are built using direct recursion. That means the method is calling itself. Indirect recursions, the method that call another method, and eventually the result will be back to the original method that's called. So that's where sometimes you see this on the lab number 6. We ask you to find the public method and then call a helper method that's private, for example, to do the job for you. That's called indirect recursion. Tail recursions, the recursive algorithms that end with a recursive call. And we have infinite recursions, And in this case, for any recursive call, you're going to start another recursive call. These are the four most famous types of the recursion method that we're going to see today. Why we are learning recursions is a culture of experience. Think differently about the problem. Okay? Solving the problem are more naturally than iteration using the recursions. In the computer science, some problem more easier to solve by using the recursive algorithms. So sometimes the nature of the problem forces us to go to the recursive algorithms to solve it. And if we are using the recursion efficiently, we end up with a very simple short code solution to the problem. This is an exercise just to motivate you about the recursion. If I told you you should not look backward, and I need to know how many students on the same row behind you, how are you going to do it? You should not look backward, but you need to give me a number of the students that are sit exactly behind you. How are you going to do it? Why are you not starting from yourself by calling someone behind you? No one, that means you're going to retain 1 or 0. Okay? You're going to call, okay? We're going to solve it recursively. So this is the solution. You got number of people behind me. So you're going to ask the person behind you, how many persons behind me? So he also going to answer another person behind him. When you receive the answer, you're going to receive the answer and add +1, because the one that is behind you, you didn't count him on the numbers, n +1. If no one behind you, so you're going to retain 0. So this is the way, or this is an example of a recursive solution for the problem finding the number of people behind you, and with the constraint that you should not look backward. So in the recursion method, we have a method that is called itself. So the recursive method call different arguments. If you start with a specific argument, a recursive call should be with different argument different from the original call. If you call with the same argument, you end up with the infinite loop. Okay? So these three things that we're going to discuss now is important to keep it in your mind. For every recursive call, you can think about you have a new code, set of parameters, a new set of parameters for each recursive call. Yes, the method is calling itself, but each recursive call, you can think about I have a new code, I have a new set of parameters, and I have a new set of local variables that I need to initialize. These three things, if you keep it in your mind, you will be able to trace any recursive methods. At each recursive call, we have a new code, a new version of the code, a new arguments, and also a new set of local variables. After completing the recursive call, we should go back. Calling back must be executed completely. You cannot retain from the recursive call, okay, before you complete the execution. The execution of the previous will begin from the point immediately follow the recursive call. These three things, keep it in your mind whenever you finish the recursive call. You cannot finish the recursive and retain until you finish the execution of the recursive call. Once you are retaining, you have to return to the call method, and the execution will start immediately after the recursive call. This is the famous example. Very classic question. Factorials. how you calculate the factorial. Factorial of n is equal to 1 times 2 times 3 up to n minus 1 times n. This is the recursive definition. In mathematics, in the school or at university, calculus, we use the recursive methods without knowing that we are actually using the recursive methods. See, the function is defined in terms of itself. F of n is equal to 1 if n is equal to 0. But if n is not equal to 0, is equal to n times, again, f of n minus 1. So the function here is defined in terms of itself. So this is the recursive. So if n is equal to 0, I know the answer immediately. It's equal to 1. If n is not equal to 0, I have to do the recursive call. I have to do every time, take n and then multiply by f of n minus 1 until I reach n is equal to 0. If I reach n is equal to 0, I know the answer immediately. So if we would like to write Java program to implement the factorial without any recursion or any recursive implementation, we end up with iterative approach. Iterative approach where the loop, for loop, while loop, okay, are used. So you can see here, we start the method by defining integer I, and factorial is equal to n, and we receive integer n as an argument. And then we go for loop from n minus 1, okay, up to 1. You see the decrement inside the loop? So we multiply always n times n minus 1 at each iteration until we reach I is equal to 1. Then we multiply with 1 and exit the loop. So we start the loop from n minus 1 up to 1. And at each iteration, we just calculate n times n minus 1. Any question about iterative approach? Everybody understand the iterative approach to calculate the factorial. So now we will see how we can do the method using the recursion. Actually, we're not going to do too much effort to figure it out. It's exactly match the definition of the mathematics definition for the recursions, because the mathematics was defined in terms of itself. You can see here, we start with what we call a base case, a case where we're going to stop. If I know n is equal to 0, I'm going to retain 1. Otherwise, else, I'm going to do retain n times factorial. Now I'm calling the function itself factorial of n minus 1. So I'm going to do the recursive call. That's exactly the recursive method. Is match exactly the mathematical definition for the factorials. So you can see here, we do the direct recursion or indirect recursion. We're doing direct, the method is calling itself. So this is a direct recursion. Okay, so this is the recursive call. Whenever n is not equal to 0, I'm going to do this recursive call, n times factorial of n minus 1. Any recursive method has two main components. Okay, we have base case or one or more base cases, at least one. Otherwise, we're not going to stop. So any recursive method, if someone give you a recursive method, you start looking for a base case. Do we have a base case? Is there one or more base cases? Also, you're going to look at the recursive cases. Is there any one recursive case or more recursive case? Okay, at least you should see one. Okay. So the base case is the very simple version of the problem that you know the solution immediately. Like factorial of n is equal to 0. I know the solution is equal to 1. I don't need to do the recursive call. So the value of the input variable for which we perform no recursive call. Factorial of n is equal to 0. I know the answer is equal to 1. I don't need to do the recursive call for the base case. So the solution for the simple case of the problem, factorial of 0 is equal to 1, this consider as a base case. You might have in your problem one or more base cases. In this case, factorial, we have only one. Factorial of 0 is equal to 1. Every possible chain of the recursive call must eventually end with the base case. If you not see the base case, or your method doing a recursive that will not end with the base case, you will end with infinite recursions. You run out of memory and you're going to have a blue screen in your computer, a stack overflow error. So the base case is the small version of the problem that can have the solution immediately, or you can tell the solution immediately for this problem. What is the recursive call? Recursive call is a call to the current method. Every recursive call should do one step toward the base case. If you're not doing any progress to the base case, this is not a recursive call. The recursive call, you define the base case in your problem. Then the recursive call should do one step, or maybe more than one step. In general, you should go toward the base case. You should do some progress to reach the base case. So some algorithms have more than one base case, okay? But at least one should be there. At least one recursive call should be there. The critical part of any design for a recursive method is identify the base case and identify the recursive call. Sometimes it's good to visualize things. When we visualize it, we understand it more. To visualize the recursive call, we're going to use the stack, which is actually used by the computer when the recursive call is done. The stack has two main operations: push to the stack, to the top of the stack, and bob up from the top of the stack. You go to the cafeteria, you have the trays, they are on the stack. You take the trays from the top of the, you don't take it from the bottom. You insert from the top, okay? So you push and you pop from the stack. Just to visualize the behavior of the stack, this is a stack, is an empty stack. At time t is equal to 0. You push 2 to the stack. You just insert one item with the value is equal to 2. Then you push 8. You insert another item. You see, when you push in the top of the stack, you not push in the bottom of the stack. So in the top of the stack. So the push 2, then push 8. 8 will be on the top of 2. If you need to take an element from the stack, you will take pop. It will retain 8. 8 is the top of the stack. Then you bob out the 2. The stack is retained empty. This is how the stack is: insert the element inside the stack and take element from the stack. Always we insert on the top of the stack and take out from the top of the stack. Now, if we need to trace the recursive method, that is factorial we designed on the previous slide, and someone asked, I need the factorial of 3. So in the stack, actually you have the main algorithm or the main function, okay? That is calling factorial of 3. Now factorial of 3 in the top of the stack. You go to the method and you ask factorial of 3. If number is less than or equal to 1, I'm going to retain 1. That is the base case. Otherwise, I will do the recursive call. 3 times factorial of 2. And that is the case. The number that I have now is greater than 1. So I'm going to do the recursive call. So there is a recursive call here. So we're going to call factorial of 2. So now 2 will be in the top of the stack. Now we have a new version of the local variables, a new arguments. You see here, we start with n. We reduce the input argument to 2. We make one step to the base case where number is equal to 1. So we start with a 3. We reduce the argument to 2. And we call the function itself. We call factorial again. We are now inside the factorial. Is the number is less than or equal to 1? That's not true. So we're going to do the recursive call. Another recursive call will be inserted on the top of the stack. So in this case, we have factorial of 1 in the top of the stack. Now we're going to do the recursive call if 1 is less than or equal to 1. That's true. So we're going to retain 1. There's no more recursive call. The immediate solution or the base case, we reach it. You can see now the recursive call. We start with a 3. We take one step to the base case, 2. Then we take another step to the base case until we reach a factorial of 1. Yes, factorial of 1 is the base case in this scenario, so we retain 1. Now we have to retain to the previous call. We cannot retain from factorial 1 up to factorial 3. Who is calling factorial 1? Factorial of 2. We're going to retain to the factorial of 2 immediately after the recursive call is retained. Okay? So we're going to retain at this point factorial of 1. 1 will be retained here 2 times 1. So now we retain to the factorial 2. 2 times 1 is 2. 2 times 3 is 6. Then this will be retained to the main function. This is the trace or visualization of the recursive call. You can see here all the component of the recursive call is there. The base case, the recursive call, and each recursive call should make a progress toward the base case. Otherwise, we end up with infinite recursive call, and we run out of the stack. In the computer, we have the stack. The stack has a size, limited size. If you use all the size of the stack, you will receive an error of stack overflow, and the computer will be stopped, crashed. Okay? Any question? We will come across that later on. We can calculate the iterative approach time complexity, and we can calculate the time complexity for the recursive call. But it's very soon now to discuss this. Okay, let us proceed with understanding the recursive methods, the component of the recursive method, try to trace the recursive methods, and understand it, how we can build it. Then we discuss one of the topics about time complexity. Yes? No. It's always the call is on top of stack. You can see here the main function is already on the stack when you run the Java. So the stack is already have some even operating system functions is running in the background. Okay, you need to go through the advanced assembly code and hardware programming and to flush the stack, and I don't know, that will cause a lot of problems. Okay, but you can demonstrate this kind for embedded systems where it's very limited operating system is running in the background. Its limit about the size. Every time you call the recursive call, you call with some new arguments. Okay, you define a new local variables. So each time of the recursive call, you're going to reserve some part of the stack. If your recursive call is very expensive in terms of the memory, you might not be able to do too many recursive calls. Okay, this is another way to visualize the problem or the recursive call. Is a tree. recursive tree. You can see here, we start with the factorial of 4. The factorial of 4 is calling factorial of 3, and then 2, then 1, then 0. In this case, the factorial of 0 is the base case. Once we reach the factorial of 0, we go backward to do the back from the recursive call. This is another way to also visualize the recursive or the trace the recursive method. It's called decompositions. You start with factorial of 4. You do compose the problem to factorial of 3 times 4. Then factorial of 2 times factorial of 3. Then factorial of 1 times 2. Now you reach the base case, factorial of 1 in this case. So then you do compositions. The first step is decomposition. The second step is composition. You now collect the result from the recursive code. So then factorial of 1 is equal to 1. Then factorial of 2 is 2. Then factorial of 3 is 6. Then factorial of 4, you reach it 24. So all these methods, either to use the stack method to visualize the recursive call, or using the tree recursive call, or use composition and decompositions to visualize the recursive call, that will help you to trace any recursive call. Now, you can see here, this is an example. I would like you to take 2 minutes and, based on the previous discussion, try to do it using pencil and paper. Here we have to print the stars. We receive n as an argument, and the tradition or iterative approach to print a star, n stars, we go through the loops from I is equal to 0 until we reach I less than n. Then I plus 1, we print a star. Once we finish the loop, we're going to print a new line. So if we call this method print star with n is equal to 5, so we should see on the screen 5 star printed, then a new line. If we call it with 3, we should see 3 screens. If we call it with n is equal to 0, we should see no screen, just a new line. Okay? So given this iterative approach for you, and it's already implemented, and it's working, now I would like you to take 2 minutes and try to solve this problem recursively. You should solve the problem without any loop. That is also another constraint for the lab number 6. Any solution submitted on the lab number 6 where the loop is used receives 0. Okay? So you have to make sure that lab 6 is all implemented recursively without using loop or while loop. Yes? Try to do it with pencil and paper. I give you 2 minutes. Final exam will be like this. A problem will be given to you and you have to do it by pencil and paper. That's a helper method. Yes, some of them you need, and I give you example on the cover page for the first one. Not all of them. Some of them you don't need. But in case, I told you, you should not use a loop inside the helper method either. No loops in the. That's yes, it's somehow you implement the problem using indirect recursion, because the main method is calling another method, which is the helper method, to do the problem. Okay? And then eventually the result will be back to the original method. Yes, it will not be able to do the recursive method. You should remember what we discussed on the previous slide. You should be able to identify the base case. You should be able to identify the recursive code. And you should make sure when you write your code in the paper that each recursive call is do a progress toward the base case. Okay? If you didn't do it, okay, you will find a problem. Okay? You have to try. Okay? You can use pencil and paper. I don't ask you to do it in the computer. Just write down. Write down. We'll give you 2 minutes. We're going to see the solution at the next slide, okay? And we're going to discuss it. But it's better to practice, okay? Recursion is one of the hardest topics, okay? And I'm not sure, maybe some of you already got familiar with this topic in the previous course or some prerequisite, but for some of you, this is a new topic, okay? Okay, so let us start. I think some of you have already put some draft notes. So we can think about handling not only one case, more case. Maybe the initial thinking is saying, okay, if n is equal to 1, I will print 1 star. If I have n is equal to 2, I will print 1 star. Then I call the same method again, but n is equal to 1. I do the same. I have the base case, and I'm doing the recursive call. Then I ask if n is equal to 3, I'm going to print a star. I'm calling the same method with n is equal to 2. And if n is equal to 3, 4, I'm going to do the same thing. When I'm going to stop? Okay? Yes, you have identified the base case, and you have many, many recursive calls. They will not end. Such kind of design for a recursive method is not efficient, okay? Because we don't know how many n we have, okay? And when we're going to stop. If you're going to do always if statements, and yes, we are calling print star for 1, for 2, for 3. This is not efficient. How we can implement this efficiently? We can identify the base case. If n is equal to 1, I'm going to print 1 star. Else, I'm going to print 1 star. Then I'm going to call the same version of the problem, but with n minus 1. Okay? So all the recursive call in the previous slide is compound in one recursive call now. You can see now I'm calling a print star with n minus 1. So if I start with n is equal to 4, then n minus 1 will be 3. So a new argument, 4, 3, then 2, then 1. Then each recursive call, I'm reducing the argument. I'm moving through the argument until I reach the recursive call, base case. So each recursive call make a progress toward the base case. This is maybe more efficient. When we identify the recursive call, if n is equal to 0, we're going to print only a new line. Otherwise, we're going to print a star, we're going to call n minus 1. So this is because the previous one, did the previous one print a new line? Yes. When n is equal to 1, we're going to print a star and a new line. Here, we identify n is equal to 0 as a base case, and if n is equal to 0, we're going to print just a line, and then we call for n minus 1. Okay. In this course, we're going to ask you to design a recursive method, but also we're going to ask you to trace a recursive method. A recursive method is given to you here. Before we start, we need to make sure we not end up tracing what? Incorrect recursive method. So we need to make sure this recursive method is not an infinite recursion. So we need to look, is the base case exist? Can you identify the base case? What is the base case? N is less than 10, we're going to retain n. That is the immediate solution. Otherwise, we have the recursive call. How many recursive call we have? One recursive call. Is the recursive call is reducing or making a progress toward the base case? You need to prove it, yes? How? You start with n, then you call mystery with a plus p. What is a? What's p? What is a? So let's say n is equal to 75. What is a in this case? If I 7, because n divided by 10 is integer division. So 7. What is p? 5. So 7 plus 5, 12, which is less than from 75. So we are going toward the base case. Now, if I ask you what is the result for mystery 648, can you tell me? Can you trace using a trace diagram, using composition, decompositions, to find this answer? Take 1 minute from your time and try to find the answer. It could be. Or it could be multiple choice. What's the trace diagram? That's the one we showed in the previous slide. This is the trace diagrams. This is a composition, decompositions. This is the way of tracing this is a stack. This is the way of tracing the recursion methods. Okay? Any answer of these will be accepted. If I ask you to trace it or visualize the recursive call, if you give it to me as a stack, okay, will be accepted. If you give it to me as a trace, recursion tree, it will be accepted. If you give it to me as a composition, decompositions will be accepted. Okay? So which one you pick will be accepted if I ask you about visualize or trace the call to find the answers. Okay? All these will be accepted. But now we are asking you to find the answer. Did anyone come up with the answer? Yes? 9. Okay. So the answer is 9. We start the mystery by calling 648. That is the first version of the recursive method. Each time we have a new code, new parameters, new local variables. So A will be 64, B will be 8. Then we do the recursive call for 72. We start a new recursive call, a new argument, 72. We calculate a new A and P. The old A and P, we don't have access to them. They are values they already set in the previous call. This is a new A, a new P. What is value for A? What is value for B? Is 7 and 2. We do the recursive call again. And 9. Now, 9 is less than 10. This is the base case. We know the solution. We retain 9. We retain back to the previous call. Retain to the previous call. We retain 9, finished. Now, this is a design problem. We ask you to have the file, read the file, and print the lines in reverse order. So this is the input file. We have line 1, line 2, line 3, line 4. You're going to receive these, and you need to print them out in reverse order. So line 4 will be the beginning, then line 3, then line 2, then line 1. These questions we need to ask ourselves about it before we start. What is the case that we are considering here? The base case and the recursive call. What is the smallest version of this problem? We are asking you to read the file and print the line in reverse orders. What is the simplest case of this problem? 2 lines. What about empty file? Yes, but this is that's the base case. Yes? An empty file. If I have empty file, I'm going to do nothing. Or a file with only 1 line. If you have a file with only 1 line, you need to reverse it. If you have a file with just only 1 line, the job is done. Yes? So let us see. We receive the input file, and we say if the input has a next line, then I'm going to read it, save it inside the line. Then I'm going to do the recursive call, reverse lines. Reverse line is the name of the method. I'm going to give an input again. So I will give you half a minute to look at this method and tell me if this is complete or not. This is input file. This is a recursive. This is input has a next line. You ask if the input has a next line. Okay? When the recursive call is going to come back, the execution will immediately follow that recursive call. Okay? The first line will be read, and we will store inside the line. Then a new recursive call is, that's the way we got confused. You got confused because you have to understand each recursive call has a new set of local parameters, new arguments. Okay? So in the first recursive call, you're going to read the first line. You're going to store it inside line. Then still there is some file. The file contains some other lines. You're going to call another recursive call and new parameters. When the file does not contain anything, you're going to retain back. When you retain back, you're going to print the line that you stored in the previous step. Where is the base case? The base case, if we don't have any next lines. If we don't have any next lines, we're going to finish. Yes. So let us see. This is the input file, and this is the output file. We call the reverse line. This is the first call. So we're going to start. We're going to read the line, number 1. Yes? And then we start another recursive call. So we read the first line. So the pointer is moved to the line number 2. And we start a new call for the recursive reverse lines, a new code, a new set of parameters, a new set of local parameters, a new set of arguments. So input is now is changed, is reduced. So has the input next line? Yes, it has a next line. Read the line. It will read line number 2. It will move to the line number 3. And now we're going to do the recursive call. We do the recursive call with the line. There's only 2 lines in the file. So we have next. We're going to read line number 3. Then we're going to do the recursive call again. Then we read line number 4. Then we call the file, last one. We don't have any next lines. That was the last line, which is the line number 4. So we should now retain. You remember the previous call, factorial of 2 was on the top of factorial of 3. So we have to retain to the factorial of 3. The same scenario here. So in the top of the stack, we have this method. Now this method has nothing to read. It should retain. It retained to what? To this method. The execution will immediately follow the recursive call. We retain here. We are sitting here. We retain from the recursive call. What we should do? Print the line. What is the value of the line? Line number 4. That will be printed. And again, we're going to retain. Retain back. We're going to start the execution at this point. At this point, what is the value of the line? Line number 3. We're going to back from the recursive call. Immediately follow the recursive call. We retain here, so we're going to print the line. Line number 2, we retain. We print line number 1. We retain back to the main function. So each recursive call make progress toward the base case. Each recursive call has a new set of arguments, a new set of local variables, local parameters. So one of the other famous examples that can be solved recursively is a Fibonacci numbers or Fibonacci series. Fibonacci series, either you think about it as start from 0 or start from 1. In this case, we look at it as start from 0. So the Fibonacci of 0 is equal to 0. Fibonacci of 1 is equal to 1. And then you can see here, Fibonacci of n, to calculate the Fibonacci number of n, you need the previous 2 values. You need n minus 1 plus n minus 2. So this is a recursive call. You can see here a Fibonacci of n minus 1. You do a recursive call for n minus 1. Then plus Fibonacci of n minus 2. So you do the 2 recursive call to be able to calculate Fibonacci of n. Okay? And that's the series. It starts from 0 in this case. I told you some people in the literature you saw the Fibonacci start from 1. Okay? But the same thing. So Fibonacci of 0 is 0, 1, 1, 2, 5, 3, 5, then 8, and 13, and 20. Each Fibonacci number depends on the previous 2 Fibonacci numbers. And this is the mathematical equations, which is exactly match the recursive implementation if we need to implement it in Java. So here the Fibonacci of 0 and Fibonacci of 1 are the base cases. So if we would like to do it iteratively, that can be done like this. If n is less than 2, we identify n as a value less than 2, we're going to retain 1. Otherwise, we define answer as a local variables and the previous Fibonacci and the previous 2 Fibonacci numbers. We initialize the previous one by 1. We initialize the previous 2 by 0. Then we start the loop. The loop starts from k is equal to 2 until we reach n. And each iteration we increment k by 1. Now, we calculate the answer by using the previous Fibonacci plus previous 2 Fibonacci, and we update inside the loop the previous 2 Fibonacci and the previous Fibonacci numbers. Okay? Until we reach the answers. Okay? I encourage all of you, when you are at home, take this code from this slide and try to put it inside the Java and run it, and try to give different value for the Fibonacci numbers. Try to give for small value, very large value, and see how much it will take for your algorithm in iterative way to calculate the value. If we would like to define it as a recursive method, we look at the mathematical definition of the Fibonacci number, we match it exactly the same. So if n is equal to 1 or n is equal to 0, we're going to retain n, because that is the Fibonacci of 0 is equal to 0, and Fibonacci of 1 is equal to 1. Otherwise, we're going to do two recursive calls. In this case, we're going to do recursive call for Fibonacci n minus 1 and also for n minus 2. So we keep calculating the Fibonacci number by doing two recursive calls each time. Once we reach n is equal to 0, we're going to stop, or n is equal to 1, we're going to stop. This is a visualization or execution trace for the Fibonacci of 4. So we have a decompositions. We start with 4. We have Fibonacci of 3 and Fibonacci of 2. Then Fibonacci of 3 will give us Fibonacci of 2 and 1. That will end with Fibonacci of 2 is equal to 1 and Fibonacci of 1 is 1. And we do the compositions to calculate that Fibonacci of 4 is equal to 3. Now I would like you to think about this problem and try to find the solution for this problem. Someone interested to count the number of zeros in any numbers. So I give you the numbers 2, 0, 3, 0, 20, 30, and I ask you how many zeros inside this number. You told me 2. Can we do this recursively? Can we count the number of zeros in any given numbers recursively by looking to the numbers and identify if the digit is 0, we're going to count it. If the digit is not 0, we're not going to count it. So if we walk through this example together to analyze it, how we can analyze this example? If n has 2 or more digits, then the number of zeros inside the number will be the number of zeros inside n minus 1 digits plus 1 for the last digit if the last digit is equal to 0. If the last digit is not equal to 0, we're going to add 0. So we look at the number. How many digits inside the number? Let's say n digits. Okay? So the number of zeros in n digits is equal to number of 0 in n minus 1 digit plus 1 if the last digit is equal to 0. For example, if we have 20030, the number of zeros in 20030 is equal to the number of zeros inside 2003 plus 1, because the last digit is equal to 0. In this case, 20031, the number of zeros will be the number of zeros in 2003 plus 0, because the last digit is not equal to 0. You can see now how we can break down the big problem to smaller problem by reducing the size of the number of digits, and then investigate and focus on the last digit of the numbers. Okay? So the number of zeros inside number n, okay, is where the number n has k digits. Okay? So the number of zeros in the first k minus 1 digits plus the last digit. What is the value for the last digit? If it's 0, we're going to add 1. If the last digit is 0, we're going to add 1. If the last digit is not 0, we're not going to add anything. So what is the base case? N has 1 digit. That is the base case. Okay. Can you complete? Take 1 minute and try to complete it. We discuss it, we analyze it, we know what's the base case, and we know how we're going to break it down. Can you complete this one? Take 1 minute. Okay. So first thing, if n is equal to 0, we reach the base case. The number that we are trying to test is actually is equal to 0. So the 0 count will be equal to 1. Otherwise, we're going to ask if n is less than 10, so that means we have a digit from 1 to 9. And the digit, one digit from 1 to 9 contains no 0. So the 0 count will be 0. Otherwise, we're going to take the n mod 10. We take the remainders, okay? And if the remainders is equal to 0, okay, what that means? The last digit is equal to 0. So we're going to call the number of 0, this is the recursive call, with n divided by 10. What is this will end up? Reducing the arguments. Now, if we start, let's say, with 200, then we're going to end up here. That's 200 mod 10 is equal to 0. So we are inside if statement here. The number of zeros inside 20, because 200 divided by 10, we remove the last digit. So we end up with 20, only 20, n minus 1 digit. So, or k minus 1 digit. So this reduce the recursive call input arguments. That means we are going toward the base case where n is equal to 0 or n is less than 10. We have two base cases here. And we add 1. Otherwise, we're going to do the recursive call, but without adding 1, because the last digit is not 0. Let's say you start with 205. 205 is not the base case, is not less than 10. The remainder is not equal to 0. The remainder is 5. The 5 is the last digit. We get rid of it by dividing n divided by 10. So 205 divided by 10 will end up with 20. Okay? Because this is integer divisions. Yes? So we call with 20. And at the end, we retain the 0 count. Any questions? You can see here we have two base cases and we have two recursive calls. Okay? Any question? Okay. So if we would like to trace the execution of this algorithm, let's say we call with 2005. So the first call will go to 5 as a remainder. So we're going to end up with non-zero, the last digit. Then we're going to reduce 2005 to 200 because we take n divided by 10. Then we're going to do the compositions. That's 20, and the last digit is 0. Thus, we end up with adding the 1 to the recursive call. And then we have 0 and 2. Then we have reached the base case where the digit is less than 10. So we do the composition now. We back from 0 plus 1, then 1 plus 1, that's 2, then 2 plus 0, and we end up with number of 0 is equal to 2. So this is how we trace the execution using decomposition and composition tree. So the recursive method is a method that's called itself. Okay? Always we have different input arguments. So if you do the recursive call with the same input arguments, that means you're going to end up with an infinite loop. Recursive call itself with a new arguments. Argument should be take you to the base case. Make a progress to the base case. Yeah. So each recursive call, you have to remember that a new code is there, a new set of parameters, and a new set of local variables is there. Now, for any recursive call, you have one or more base cases, you have one or more recursive call. This is an example. If you ask someone about factorial of 1, you're going to ask your brothers or your friends, you're going to ask his father, you're going to ask his mothers, what is the factorial until they reach, what is the factorial of 0. They ask each other until they reach factorial of 0. Nobody knows what's factorial of 0. They ask the big guy, he knows what factorial of 0 is equal to 1. He holds the base case. That is where the stop of the chain of the recursive code. If the recursive call is continue, that is infinite loop. But the recursive call ends with the base case. He has the key. He has the factorial of 0 is equal to 1. Then everyone know the answer now recursively. So we know the answer by calculating. We know factorial of 1. Then 1 times 1 until we reach the factorial of 4 is equal to 24. This is how the recursive call is working. Someone or some part in your method, you hold the recursive call, which is the solution for the simple version of this problem. You can find the solution immediately without doing any recursive call. There is no recursive call to calculate factorial of 0. We know the solution immediately. We stop the chain of the recursive call, and then we go back through the chain of the recursive call until the first caller to find the answer. Let us see this recursive problem. We would like to calculate x to the power y recursively. So I give you x, and I told you power of x to the y. Okay, so we can do this iterative. This is how we do it iteratively. We start the product is equal to 1. You cannot start a product is equal to 0. We'll end up with the result is equal to 0. So we have input x, we have input y. We go through the loop from I is equal to 0 until I is less than y, I plus plus. Then we make the product times x. Then we retain x. If I ask you to take 1 or 2 minutes and write down the recursive approach for or recursive solution for this problem. We can assume a precondition that x is greater than 0, but you can have x negative, y is negative, there's no problem. X to the power 0 is equal to 1. Yes? X to the power 0 is equal to 1. If x is 0, whatever x to the power 0 to the power 100 is 0. Yeah? So the base case in this case, n x is equal to 1. Okay, but you are raising x to the power y, not reducing x. You're not calculating factorial. Okay, so let us start. We identify that power of x to powers of 0 is equal to 1. Yes? Otherwise, we're going to do power of x to the power of y is equal to x times x to the power y minus 1. Okay, if x is greater than 0. So this might be the solution here for x and y. So if y is equal to 0, the condition here is y is equal to 0, we retain 1, not x is equal to 1. So we have a recursive call, one recursive call, x times power of x to the power of y minus 1. So you can see here in the recursive call, we reduce the power by 1 each time we do the recursive call until we reach the base case where y is equal to 0. So this is how we end up with the recursive call if we call it with power of 4 to the power of 3. We have 4 times power of 2, then power of 4 to the power of 1 until we have power of 4 to the power of 0, and we retain from the recursive call 1, 4, and 4, and to calculate 64. Now, what if I modify the problem a little bit? I say I have no limit for y, or in this case n. N can be 0, n can be positive, n can be negative. What is really going to be changed in the previous implementation? What we're going to do, any change on the previous implementation, or we have to start a new implementation with a new base case? So here you can see if n is positive, nothing is changed, the same implementation. We end up with reducing n, each recursive call, n minus 1, until we reach n is equal to 0. But what about if we have n is negative? Now, we need to calculate x to the power minus n, which is equal to 1 over n x to the power n. I would like you to see how the problem of x to the power minus n is defined in terms of x to the power n. So simply we can have the same previous algorithms with the same base case, but we modify the recursive call. We're going to look at the n. If n is greater than 0, we're going to do the same thing. We're going to calculate x times power of x, where x with n minus 1. So the new argument is reduced. And then we have another recursive call where n is negative now. If we have n is less than 0, so we're going to do 1 over power of x, and we're going to do the recursive call, but this time we're going to reverse n to minus n. So we just modify this. This will be one call, then after that we'll be end up with here inside the recursive call. When this is finished, we're going to return back to this one where n is negative. So this is a small modification to the problem, but it also is defined in terms of the previous problem. I would like you to take 1 minute and try to trace this mystery recursive call. So we have x and y, and we identify the base case. When x is less than y, we're going to retain x. Otherwise, we're going to call the same method, but with x minus y, and then we have y. 2 arguments, x and y. What we have the result if we call for mystery 6 and 13? Immediately it's 6. What about 14 and 10? 4. 37 and 10. 8 and 2. No routine? 1. What about this one? What about the first one? What are you going to print in the first one? 1. One. When you do the recursive call, you're going to go back immediately after the recursive call, and you're going to print n. What is n? Is what you start with. So the first time you start with n is equal, when you call the mystery 2 with 2, you start with n is equal to 2. N is greater than 1. So 2 times divided by 2 is 1. So when you come back from this, n is equal to 2. So you're going to print 1 and 2, 1 and 3 here, 1, 2, 4, 1, 2, 4, 8 and 16, 1, 3, 7, 15 and 30, 1, 3, 6, 12, 25, 50 and 100. Okay, so I will leave some of these for you in the slides. We'll stop here and we'll start next lectures.